So Kirk, are you in US or in Chile, stuck in Chile?
No, I've been at home for several months. I've been working on my vegetable garden very much, and some household things, and the rest of it is all writing and reviewing papers. Oh my God.
Hi, Kirk.
Hi.
Hi, Kirk.
Hi, Maria. How are you?
Maria from Portugal.
Yeah, from
Fine, thanks.
Are you still in Gaia?
Yes. Reading your papers, the old ones and the new ones. Always.
Is that because you're having trouble going to sleep?
No, because they are very, very good, always.
Jocelyn, I have a question.
Yes.
Maybe I can show the first slide of my PowerPoint presentation where I have the title of the project.
Yeah. We shared the links already on the chat. There are two links. One is for our presentation and the other is for the YouTube channel if you want to subscribe, because all our videos are going to be kept there. Yeah. And yeah, you're going to share. Yeah.
Just to Can you see the can you see my screen?
Yes.
Yeah.
Yes.
Perfectly.
Okay.
Good evening. Or good morning, sorry.
Jesus, good morning, Jesus. Jesus is from Spain.
It's fine.
Good morning.
Hello, good morning.
Jesus, habla inglés?
Sí.
Okay.
I can speak in English.
Good. Welcome, Jesus.
Thank you very much.
I also have greetings from Virginia Siminelli from Brazil.
Mm-hmm.
I sent an invitation, but she's teaching right now, so she can't be here.
You see, Maria Eugenia is also there.
Okay. Okay, I think we are ready to start.
Yes, we're ready.
Okay.
Everything's working.
Okay, cool. YouTube is working? Yes. But I need to exit. Oh. I need to exit my full screen.
Okay.
Yeah, because I need to read my introduction a bit. Well, it's okay. Well, hello, everybody. Thank you very much for being here today. This is the second webinar organized by the IGCP 707 project, which is called Origin, Distribution, and Biogeochemistry of Arsenic in the Altiplano Puna Plateau of South America. This project is funded by the UNESCO in collaboration with international associations. And this year, the pandemic didn't allow us to make the annual meeting that we are supposed to do. So we decided to interact by making these webinar series, and which are open to the scientific public and also students. The leaders of these projects are Jocelyn Tapia from Universidad Católica del Norte in Antofagasta, Chile. Hello, Jocelyn. Is Mauricio Ormachea from Universidad Mayor de San Andrés in La Paz, Bolivia. Hello, Mauricio. Also, Noemi Tirado. I'm not sure if Noemi is here. Also from La Paz, Bolivia. Kirk Nordstrom, who is our speaker today, and me from Universidad Nacional de Salta and CONICET in Argentina. So this project is part of the International Geoscience Program of UNESCO. And well, this project is dealing with global issues like arsenic, and we have cooperation between scientists from the North Hemisphere and the South Hemisphere. And we hope that with this project, we can bring some benefit to society, capacity building, and sharing knowledge between scientists. So before I introduce our speaker, I want to introduce Anne Meist. Hello, Anne. Well,
hello, everyone.
Because today we have many Spanish-speaking people, Anne is going to help us with the translations. So if somebody wants to write the translation in Spanish on the chat, and also if you want to ask orally the question in Spanish, Anne will be able to translate. Anne is right now in the same room with Kirk, respecting the social distance. So they can interact each other and they can help us for the question and answers session after Kirk's talk. Anne has a PhD from Princeton University in geochemistry and has substantial experience working on water pollution associated with metal mines, including work in South America, especially in Peru. That's why she's very good in Spanish. She's a consultant working for Buca International. Today, our speaker is Kirk Nordstrom. He's a senior scientist with more than 40 years with the United States Geological Survey. He has a bachelor's degree in chemistry from Southern Illinois University, a master's degree in geology from the University of Colorado, and a PhD in applied earth science from Stanford University. With more than 250 publications, Kirk is recognized internationally for his research on acid mine drainage, radioactive waste disposal, geothermal chemistry, geomicrobiology, arsenic geochemistry, thermodynamics, and geochemical modeling. Well, for us, it's a pleasure to having Kirk today. So I hope we all can enjoy and ask as many questions as we have. So.
Kirk lost his connection temporarily, hopefully, and he's trying to get it back.
Okay.
Okay.
I was just sharing my.
Es un computador del gobierno. Es porque no es muy bueno.
Ah, está bien.
Oh, no, because then you'd have to share.
For those that maybe can't connect to the Zoom, you can also watch. You can also watch it on YouTube. Jocelyn, I think it's not working.
The YouTube is working, but I think I put a wrong link. I'm sorry.
Ah,
Yeah.
but I have opened the
Oh, it's working or not?
meeting that we are supposed to do. So we decided to
Jessica, he's putting the presentation on a memory stick and we'll put it on my computer.
Okay.
So it'll take a couple of minutes.
Okay. Okay, I'm seeing now the YouTube presentation.
It's working. The thing is, I put two links. One is for the YouTube channel, the second link, and the first link is the presentation.
Okay.
Yeah, I'm watching the presentation.
Okay. Yes, me too now. So for the people who is watching on YouTube, they can also ask questions on the chat and I can read the questions and ask. So how many are we today, Jocelyn? 200?
Soon we have 85 already, and there were 227 subscribers. Okay. Yeah, we're going to start.
Okay. Can you see my screen, Jessica?
Yes.
Yes.
Perfect.
Okay. Okay. Let me do it in the presentation mode. Okay. All right. I think you don't need this thing because yeah, it's just okay. Yeah. And then we'll have to yeah, there we go. Okay, they should hear you.
I've just had a gender change. Can you see me okay? All right, let's try it. Jessica, I can see you. So give me a thumbs up. Your change. Can you see me okay? Okay. Okay, now mute. All right. Sorry for the technical problems, but it is a government computer and that these things happen occasionally. So this is an overview for arsenic hydrogeochemistry because it's an overview and because I'm trying to cover all of these things, tectonics, lithology, hydrology, microbiology, and chemistry. It's a very brief overview of all these things that I'm trying to summarize in about 45 minutes. We'll see how well this works. The overriding question in my mind that's bothered me for a long time is, why is arsenic more concentrated in some parts of the Earth's surface and not other parts? And there's another important question that goes along with that. Are there hydrologic factors that mobilize geogenic arsenic? So we're going to start with the big picture here. There's two ways to think about the global arsenic cycle. One way I call flux reservoir concept. And I call it a static concept, even though there's a flux involved, because it's a picture at one moment. It's just at one moment in time. And it's the mass balances for all the sources and sinks in the transport of arsenic throughout the Earth. The other one I call more dynamic, the geologic cycles concept, which is sort of like thinking of the changes in the flux reservoir concept over long periods of time. And of course, these are related, but not quantitatively necessarily. Flux reservoir is, in other words, the current mass balance, and geologic cycles are the result of billions of years of Earth history. The global arsenic cycle, according to the flux reservoir concept, has been published twice by Jörg Machelat in Germany. His first publication was in 2001. He updated it in 2011. And I'm not going to go through all the details of this. This is just to show you that this is the main picture of what it looks like. So, for example, at the top, you have the atmospheric reservoir. So that's in the atmosphere. How much arsenic is there? Total mass. And he's put in the concentration as well. And he's also put in the residence time based on what we know about fluxes in and out of that reservoir. And that's what all the arrows represent, are the fluxes. Normally, when one does a global cycle, one puts numbers on the arrows too that say what the rates of movement from one reservoir to the other are. And he has that information, he just didn't put it in the diagram. At the very bottom, you see the lithosphere, or the upper crust of the Earth, and the amount of arsenic that's there. Obviously, that rock weathers, so you have the pedosphere, or the soils reservoir, and there's arrows going to and from the hydrosphere for soluble or mobile arsenic in the hydrosphere, in the oceans and the rivers and the lakes and so on, and biosphere as well, and the anthroposphere, the things that we do to move arsenic around. So this has been done. It's a very rough estimation, but it helps tell us where a lot of the arsenic is. And it helps answer questions like how much of the arsenic in the atmosphere is anthropogenic, for example. And there's something like a couple of orders of magnitude higher arsenic in the atmosphere than what would be there from natural sources. So it's helpful for information like that. That's about all I'm going to say about the flux reservoir. I'm jumping now to the geosphere and the geologic cycle. And to get an idea on that, I've got this table that some of you have seen before. Arsenic in the bulk Earth, the best estimates we have is from Rudnick and Gao. So for the whole Earth, it's about 1.7 ppm. But they also can estimate how much is in the different parts of the Earth, the mantle and different parts of the crust. So going from the mantle is very low in arsenic, roughly 0.066 ppm. As we go from the mantle to the lower crust, it increases to 0.2, to the middle crust, it increases to 3.1, and the latest estimate for the upper crust is 5.7 ppm. So you see there's a regular progression as it increases towards the very upper part of the crust, and that tells us something about how arsenic naturally has differentiated into different parts of the Earth. So probably in the original formation of the Earth, when the core, mantle, and crust was formed, there was arsenic is considered a lithophile element, a light element that tends to concentrate in the upper crust. In addition to that, we can say that there's been differentiation caused over large periods of time through geologic cycles of continental drift, plate tectonics, subduction, and that whole cycle of erosion and back to subduction. Just for comparison, seawater has only 1.7 ppb in it. And that number is a well-studied number. We have lots of good data on that. Okay, so then we want to look at, all right, let's be specific for rock types. So I went to the standard reference rocks that are published by the USGS, and there are some that I had to go to the Geological Survey of Japan also. They have a good list of reference trace elements and reference rocks. At the top of the list is gold ore that has the highest. And this is a number from one sample they have, 180 ppm, but it can range all over the place because there can be a lot of arsenopyrite in the gold ore. And but it tells us that if you want to know where arsenic is, where it tends to be concentrated, it tends to be concentrated in hydrothermal gold mineral deposits. Now, to answer the question of why is that, we have to go to the next guy, marine shale. But before we do, I just wanted to mention at the bottom here, if you want to know where most of the world's arsenic is, go for the gold, as they say in the Olympics. And I put yin yang in there because gold is and arsenic are sort of like these opposites. Gold is this beautiful, attractive, malleable metal that everyone likes and has a high price on it right now. And the other side is arsenic, which is very dangerous, very toxic, and everyone wants to avoid. So with the good comes the bad. So why is arsenic strongly associated with hydrothermal gold? Well, there are geologic processes that cause this to happen, and there's fluid chemistry that's involved. And the fluid chemistry means that you're talking about a function of composition, pH, redox, temperature, and pressure. So the second highest on this list, marine shale, 68.5 ppm. Again, that's just a reference rock sample. To give you a better idea of the range of concentration of arsenic in shales, I've got a couple of references at the bottom there, New Albany Shale in Kentucky, USA, 11 up to 2,750 ppm arsenic. When it gets into the several hundreds to a few thousand ppm, you know right away that you've got sulfides in there, you've got pyrite, and that pyrite is mostly what's containing that arsenic. You may have some arsenopyrite, but at least pyrite you can count on. The Pierre Shale has been studied a lot in the Western United States, and another paper has a range there of 1 to 490 ppm. So you can see it covers a very large range, but there's no other rock type that has such high concentrations other than gold ore. Shales are important for a couple of other reasons. They're most representative of the Earth's crust, and they are source rocks for many hydrothermal mineral deposits. Matschullat in his global arsenic cycling estimates they're about between 2 and 5 times 10 to the 4th teragrams. Teragram is 10 to the 12th grams of arsenic in the lithosphere compared to 2 teragrams in the world's oceans. So that's where most of the arsenic in the Earth exists. And shales have been the dominant rock type in the Earth's upper crust for about 2 billion years. So it makes it a fairly important source and the largest source. And a question that's pretty easy to answer is why are trace elements like arsenic so enriched in shales? Well, shales are fine grain, consisting of a lot of fine grain clays. They have a high surface area. They absorb trace elements strongly. And secondly, they also tend to have organic carbon in them. Some of them are very carbon rich. And that means they're reducing sediments that produce sulfides like pyrite, and pyrite incorporates quite a bit of arsenic into it. And it's been shown that if you look at the relationship between the carbon concentration in a shale and the arsenic concentration, you get a nice, fairly good correlation. And many others have seen that since Turtelow's paper in 1964. So this is the first important arsenic enrichment process in the geologic cycle, absorption and incorporation into sulfides in those carbon-rich sediments. For example, there's a paper by Piper who looks at the process of seawater as being a source of minor elements in black shales and shows that for trace elements like arsenic, it's pretty clear that's what's going on. There was a special session at Goldschmidt meeting in 2012, I think that was in Montreal, that examine the relationship between black shales and mineral deposits. So over time, economic geologists have realized that black shales have been the most common source rock for hydrothermal ore deposits. And in some cases, economic geologists have shown that here's the black shale, here's how it's been altered, and over here's the ore deposit. So they can actually see the source rock, they can see the path of transport, and they can see the environment of deposition. So we have a connection between shales and ores of gold, copper, silver, lead, zinc, cadmium, etc. Now, once you have that shale with those trace amounts in them, and they get hit by a magmatic intrusion, and it starts heating up the shale, and hydrothermal fluids start circulating through it, it'll dissolve the arsenic from those sediments or from the rock. And that was first shown by Alison Mann in some laboratory experiments, and later, those are two famous New Zealand geothermal chemists. Another geothermal chemist from New Zealand, Urs, in 1977, showed that when you leached arsenic from a New Zealand greywacke, you can see it coming out at 105 degrees. But when you increase the temperature to 480, more than 70% of the arsenic can be leached out of that rock. So once the temperature goes up, there's a preference for arsenic to be in the fluid phase. That fluid phase is going to be in fractures in the rock. So fracture flow dominates, and you're leaching from a large volume of rock into a limited fracture porosity, which further concentrates the dissolved arsenic. So here you have your second enrichment process, partitioning into the fluid phase with an increase in temperature. Now, the association of gold and arsenic has another important aspect, and that's the fluid chemistry. So they're both soluble in hydrothermal fluids because sulfide complexing, that is, both of them complex fairly strongly to sulfide. That keeps them in solution, even for some range of temperature and pressure. So that's a third enrichment and solubilizing effect, is the sulfide complexing. In gold mineral deposits, the main mineral is arsenic, right? Which is pyrite. It still has the structure of pyrite, but we have an unstable connection.
I can hear you very well, Kirk, don't worry.
Okay, let me know if there's a problem.
Okay.
So arsenic pyrite is still the pyrite structure, but arsenic is substituting for some of the sulfur in the pyrite. And this was an amazing diagram from a paper by Reich and others at the University of Michigan. It shows the solubility of gold in arsenic pyrite. So one of the reasons why they mine a lot of pyrite and arsenopyrite is because it has gold in it. And sometimes it's in particles, but often it's dissolved actually in the pyrite as well. And you can see these are log scale, log gold versus log arsenic, and you can see the gold increasing as the arsenic increases in the arsenic pyrite. This is from the same paper. It shows the direct substitution of arsenic for sulfur in the pyrite. It's pretty much a one-to-one. I mean, it just substitutes exactly. The more arsenic you have, less sulfur you have in that latticite. There is a limit to how much arsenic you can put into pyrite, and it's around 10 to 12%. That's the same, roughly the same as whether it's mole percent or weight percent. But after that, the structure breaks down and it can't accommodate anymore. Now, the reason for that has to do with iron. If you change the iron to nickel, nickel is just enough difference in cation radius that now you can get arsenic substituting in that lattice site over the whole range of composition. This is an example of Rammersburgite, Gersdorfite, going from nickel arsenide to nickel arsenic sulfide, which Gersdorfite is the analog to arsenopyrite, of course. And you can see they've got samples covering that whole range. And this is another reason also why it's not at all uncommon to find nickel and arsenic associated in many mineral deposits as well. Then I went to the question of, okay, somebody must have looked at the global tectonic picture for gold deposits and why they are where they are, because that's where the arsenic's going to be, right? And there's some good papers on that. Two outstanding ones I've mentioned here, Kirian Vine and Goldfarb et al. And so you look at those and you can see it's related to global tectonics. And I'll say a little bit more about that in a minute. The excellent book by Ravenscroft et al. On arsenic pollution, he also hinted at a crude relation between tectonics, climate, and worldwide arsenic occurrence. But he didn't follow that up it was just a suggestion in his book. So here's a cross section of the Earth. And now I'm going to see if I can do a little laser thing here. Okay, right. Cross section of the Earth. Here you have your subduction zone, oceanic crust going down. Keep in mind that wherever you have this, you have all these sediments that are near coastal areas like shales that are going down there. As that stuff gets heated up and it starts interacting with crustal material, it starts to melt, form magmas, comes up, and you have your Andes and your volcanic eruptions and so forth going on. And then over here, the asthenosphere is basically the mantle, and that's coming up in two main kinds of places. One are the ocean spreading ridges you see here. So this is all new oceanic crust being formed. It doesn't have the continental sediments, so it doesn't have the same material. And we know that the mantle has very low arsenic in it, so we would expect this material to have low arsenic in it, and most of the waters associated with it should have low arsenic. Then you have hot spots that break through the crust in various places. If they break through the crust in the ocean, a shield volcano is shown here. A good example is Hawaii, of course. You wouldn't expect there to be much arsenic there either, because you don't have this crustal, terrestrial crustal material with the high arsenic in it. Over here in your island arcs, as in Japan, or stratovolcanoes, that might be in between. If you have a lot of material from the continent that got incorporated into this island arc, as you often do, you will have high arsenic. So in Japan and New Zealand, you would expect it. So the simple picture of subduction zones, mid-ocean ridges around the world, you can see here, and the hot spots are all the red circles shown. So there's Hawaii. You can see the subduction zone going all around the Pacific through South America, Central America, North America, Alaska, around to Siberia and Japan, and down into Malaysia and New Zealand. So you would expect all those areas to be high arsenic areas, but not Hawaii. And then you have Yellowstone, which is a hot spot right in the middle of the continent that should have some high arsenic in it. Iceland should be low arsenic, and so on. So by knowing something about the geology and the tectonics, you have an idea where you might expect arsenic to occur. So let's just check that out and see if it's true. There's very few analyses of Hawaiian thermal waters for arsenic, but there are some, and they only go up to about 70 ppb, which is not very high. Iceland thermal waters, they're continuing to get more data on this, but the latest numbers that I've been able to find go up to 252 ppb, but most of them are quite a bit lower than that. They're in the few tens of ppbs. Interesting thing about Iceland, the first paper on arsenic in Iceland thermal waters was by our good friend Stefan Arnason, who did both cold surface waters and thermal waters. And after he published that paper, I asked him, I said, where do you find the highest arsenic in thermal water values? I knew that there was one place in Iceland where there's some rhyolite. Most of it's basalt, but there's some rhyolite. And I said, does it happen to be close to the rhyolite? And he checked it out, and yes, it was. So again, the reason why there's rhyolite there in Iceland, which is on a mid-ocean ridge and a hotspot, is because Iceland got caught between Europe and North America which collided at least a couple of times over the geologic history. And some of that continental material got caught in Iceland at one point and got stuck there. Yellowstone, highest we've measured is about 15 ppm, typically 0.3 to 3 ppm arsenic in the thermal waters. One of the highest ones that was first recorded was from El Tachio in Chile, up to 30 to 50 ppm. And it's interesting, there's no hydrogen sulfide in that water. Alaska has very high arsenic, up to 48 ppm, and New Zealand up to 8, Tibetan Plateau up to 6, although they may have found some higher values now because they've been doing a lot more analyses there. So all of this is consistent with the general tectonic picture that high arsenic occurs with thermal leaching of continental rock, especially rock that's incorporated shales into it. So there you have the so-called Pacific Ring of Fire, where you would expect to see high arsenic. I show this picture of Alaska because it was one of the first places in the United States where they found very high arsenic in groundwater, up to 10 milligrams per liter, near the Fairbanks area. And Fairbanks is right in the middle of this big yellow envelope, which defines the gold mineral deposits of Alaska. And so this is where you would find high arsenic from the mineral deposits. And then going south from there down in this direction in the Alaska Peninsula, you start getting into active volcanoes. So those and the gold belt all have high arsenic in them. Rift valleys is the other place where you tend to get high arsenic, and the biggest rift valley that we know of on the planet is the East African Rift Valley, which is spreading continent material, continents breaking apart, spreading apart, causing this rift zone. You have the Somalian plate and the Arabian plate, the Nubian plate all separating from each other. And this rift actually goes from about Israel all the way down, and it goes down south as far as Botswana, where they have found some arsenic. And that's kind of the tail end of an old rift zone down there. It's recently been figured out. So this rift system looks something like this in the schematic cross section. As the continent is pulled apart, you get zones of weakness, magma comes up closer to the surface and creates hydrothermal fluids that rise to the surface. And those all have high arsenic. They also have high fluoride. And both arsenic and fluoride are big problems in the drinking water for several of these East African countries. There's the rift zone going down towards Botswana. That was a new development for me anyway. I didn't know that it went down there, but it does. And in this area in Botswana, there's high arsenic. And then India, Bangladesh, Nepal, Myanmar, Pakistan. How about all of that area? And again, we can explain that if we look at the geologic history, which India was formed from the Indian landmass some 70 million years ago, moving north and colliding with the Eurasian plate. And of course, causing the Himalayan orogeny and caused a lot of ore deposits and arsenic mineralization. Now, during this period of time of several tens of millions of years, there was a big sea between these two plates called the Tetha Sea. And it was a large shallow sea that would have had a lot of fine-grained sediments, in other words, a shale, that would have built up over this period of time and accumulated trace elements like arsenic. And then that got crunched into the Himalayas. And then with the heating that came with that subduction, there were several subduction zones actually, that would cause the thermal waters that came through there to have high arsenic. I love this picture because it's without all the extraneous anthropogenic activities and without all the vegetation. It's like a LiDAR map of India, and you can see it, how it collided very clearly with the Eurasian plate. And you have this mountainous areas from Pakistan all the way through the Himalayas into China. There are sulfide mineral deposits all through here, up here. We know there's a lot of arsenic in the Tibetan Plateau, and there's also mineralization in this area as well. And there's arsenic coming down into Pakistan. This is just a close-up example in Bangladesh. They've known about places of high arsenic mineralization in the foothills of the Himalayas for quite a while. For example, the copper and arsenic mines at Samthar Hill near Darjeeling, which erode into the Tista River and come down into the Brahmaputra. There's also some coal deposits over on this side in India, and they found some lollingite, which is a rare mineral, iron arsenide. So that's also weathering and going into the Ganges. So there's source material. There's also geothermal waters that go into tributaries of the major rivers of the Bengal Delta. Now, exactly how much of that and the rate of that comes down is still a subject under investigation, but people have found in many of the high elevation streams coming off the Himalayas and the Tibetan Plateau, high arsenic concentration in those waters. This just shows the mineral deposits that are now known in China. There's a lot of them, again, caused by this collision between plates. Going west from, okay. So going west from India and Pakistan, we go into Iran. There's a whole line of hydrothermal mineralization in the mountains here, and many of them are gold deposits with high arsenic. And you continue west through Turkey and Greece, Italy, and so forth. And there's many places through here that have high arsenic. And that's because the African plate collided with the European plate at roughly the same time period as the Indian plate was colliding with the Asian plate. And you had subduction zone and volcanics and geothermal, hydrothermal activity going on. All of those have caused this high arsenic zone. The most famous place that I've ever seen, I've never been there, but the Zarshuan mine gold mine in northern Iran, the entrance to the tunnel, one of the tunnels there, is just nothing but orpiment and realgar mineralization lining the tunnel, the portal. And there's a lot of gold in that, but it's also kind of lethal material to be mining. And of course, there's not any protection that I'm aware of for these miners. So that alpine Himalayan orogenic belt is the suture zone that would be prime area for high arsenic. Going to the hydrochemo side, the fluid composition, what are the factors that affect solubility and mobility? There's a lot of them. I've listed them here. High pH waters, reduced waters or organic rich, high sulfide waters, which usually go with the reduced waters, high temperature waters, as we've mentioned, high bicarbonate, carbonate waters, high phosphate waters. Phosphate is a very good competitive absorber for arsenate. And so if you have a water with high phosphate, the arsenic has a lot of, let's say the phosphate and the arsenic is about the same concentration, the phosphate will tend to outcompete the arsenic on surfaces. High silica waters also, and high sulfate waters. Some of the highest recorded values are given here. These are in micrograms per liter, so 4 million micrograms per liter. That's 4 grams per liter at the giant mine, where they've taken a few 100,000 tons of arsenic trioxide that they couldn't get rid of or sell. They put it underground in the mine, which stopped working back some decades, couple of decades ago, and put it behind some vaults, but they had no other protection. So the groundwater came through, dissolved it, and now they have this mine that's seeping very high arsenic waters in the subsurface. Iron Mountain, kind of a famous place in California, a Superfund site that I've been involved in and I did my PhD thesis on. We went underground one year and found some very acid waters with 850 milligrams per liter arsenic in it. There's a similar site in Russia, in the Urals. They documented 400 milligrams per liter dissolved arsenic. And then there's evaporated closed basin lakes, California and Nevada. And one of them, Cyril's Lake, has a borate deposit in it, but it also has very high arsenic, is another example of that, and may be analogous to some of the places in South America. Now, very quickly, I'm going to mentioned the Yellowstone and the silica factor. We've done a lot of studies on geothermal waters in Yellowstone. This is the upper Firehole River, this picture here. And I think, yeah, the circle shows where the Firehole River is on this map of Yellowstone Park, which is in the very northwestern corner of Wyoming. The Firehole River receives more geothermal input than any other river in the park. Under low flow conditions, about 30% of the flow of that river is coming from geysers and hot springs flowing into it. This picture down here is about near in the Midway Geyser Basin, so it's about partway down the river. So we did a profile of the river, going from above where most of the geysers are to the lowermost point that we could sample. You can see the temperature profile in this upper diagram, 10, 12 degrees. And then when it gets to the upper geyser basin, this is going from upstream here at 0 distance, and downstream is at 38 or something kilometers. So getting into the upper geyser basin, you see this big jump, and that's where most of the thermal water comes in right there. Jump in temperature from around 10 degrees up to 22 or so, and then it keeps going up from more input up to 25 and then on down. In that same range, you see the pH jump. That's because these geysers have high pH. The pHs are 9 to 10, and so they raise the pH of the river. They also have higher chloride than the normal river water, and so the chloride concentration jumps up as well. Now, what I wanted to show you particularly was the silica profile and the arsenic profile. Here you can see silica is less than 50 milligrams per liter at 0 point distance. And then when the geysers start dumping their hot water in, it takes a big jump up to about 90. And we analyzed both the dissolved or filtered silica and the unfiltered silica, which is this total recoverable value here. And at this point, you can see there's a clear separation between these two, where the unfiltered water has higher silica than the filtered water, telling you that there's colloids of silica that are being filtered out. In other words, silica is precipitating actively in that water. There's so much silica in there. And we also know that because the bed sediments of the river in many places are cemented by silica. You can't drive a stake through them. They don't look like they're cemented because it's very clear, thin veneer, but it's cemented with silica. So if you have that silica surface, that's sort of like, you know, if you have a beaker of water that has a lot of arsenic in it, but it's in a glass beaker, arsenic doesn't want to absorb to that. And that's what's happening in this river. The arsenic goes up and up and doesn't absorb, even though it's all arsenic 5. We've done the redox speciation on it. Now, the arsenic concentration jumps up in the same place where the other jumps occur. It goes down here because it's getting diluted by another tributary that has close to the same discharge. And then it goes up. But the reason that you know that no arsenic's being attenuated is because when you do the arsenic loading, it just goes up and up and up until you get to the end of the river where there's no more hydrothermal inputs. So the implication there would be that where you have a lot of arsenic from geothermal features coming into a river, you're likely to have sediments that are coated with silica, don't absorb arsenic, and the arsenic can travel a lot further downstream. And maybe this is one of the things that was going on with the Rio Loa in Chile. And we think some of that's also going on in the Tibetan Plateau, and the rivers coming down there as well. There are some calculations of mass flux of geothermal arsenic from Lassen Volcanic National Park. It's about 6 metric tons per year. Concentrations are low, but when you start adding it up on an annual basis, it's a lot. From Long Valley, another place where it's been measured, it's about 8 metric tons per year. I went to our data and calculated it out, and we're looking at, and for the Firehole River only, but it's the main one, in Yellowstone Park, about 80 metric tons per year are flowing out of the park. Almost none of it's being absorbed on the bed sediment, so it goes about 50 kilometers, and then it leaves the park and enters areas of farming and irrigation where they're actually using some of that arsenic-rich water. All the major rivers transporting arsenic in Asia and eroding from mineralization originate from the Himalayas or the Tibetan Plateau, where geothermal waters discharge. So we're talking all of these major rivers: Indus, Ganges, Brahmaputra, Meghna, Mekong, Red River, Yangtze, which the Chinese prefer to call Xiangjiang now. Just more recently in the Yangtze, they've not only found arsenic in the river, but in the pore waters of the sediments around major cities like Wuhan, which everyone knows now because of the virus. But in those sediments, they found up to about 1 milligram per liter dissolved arsenic just in the last 5 to 10 years. Very quickly now, the microbial part. One can't talk about arsenic and its mobility and its transformations without understanding a little bit about what the microbes do. And that's all I have time for, is a little bit. There's a lot of families of prokaryotes that can oxidize and reduce arsenic. Prokaryotes are 2 of the 3 domains of life, the archaea and the bacteria. Everything else is eukarya, which are complex cellular organisms like us. Archaea and bacteria are more like, they can be single cell, but they work as single cells and their cell structure is different. A lot of these guys can tolerate very high arsenic solutions. For example, there are studies where they found they could adapt to 15 grams per liter of dissolved arsenic. So it doesn't kill them like it kills us. They're chemoautotrophs, or more properly chemoautolithotrophs, but it's a mouthful. These microorganisms actually derive energy from oxidizing arsenic. This was shown a few decades ago. There's a lot of arsenic reducers of different types out there, and they can reduce under aerobic conditions. So I was in the laboratory of a friend of mine. He had on his lab bench a large beaker with a clear solution, and he's bubbling air through it. And he said to me, that solution, Nordstrom, is only has arsenic 3 in it. There's no oxidized arsenic. How does that happen? And I said, well, you must have a lot of dissolved organic carbon in that solution. And he says, that's right. So given a good food source of carbon, there are microorganisms that can reduce arsenic even in the presence of lots of oxygen. The more interesting thing to me was that isolates have been found that can both oxidize and reduce arsenic. The same bug can do that. And here's one of the first papers on that was published by Gehring and Banfield. This was a bacterium from Yellowstone Park, and they monitored its oxidation. This is 100% arsenic 3 at time 0. And this is the arsenic 3 curve very quickly going down to nothing. This is the arsenic 5 going up. So it's a direct oxidation of that. And this is, the crosses are just cell density, the cells growing during that time period. Okay, that's interesting, but what's more interesting is they repeated the experiment where after the arsenic 3 decreased to nothing, then they took the air out of the containers and the arsenic 3 went back up. And then they let air in again and it went back down. Totally reversible. And we're finding now that there's a lot of microorganisms that can do the same thing. It's not just a specialty for any particular strain. Here's another one from hydrothermal vents in the ocean. Redox cycling of arsenic by the marine bacterium Meridobacter santoriniensis. I mention this because it was named after Jo Santorini, who I had the pleasure of meeting one time. She was the first person to find that there were chemoautotrophs that could get energy from oxidizing arsenic. And she studied a gold mine in Australia and discovered that. How are we doing on time? Okay, I'm almost out of time. So this is a hot spring, acid hot spring, pH 2.7, 62 degrees at source, showing iron oxidation, the iron 2 going down, shows arsenic 3 oxidation going down. Now here's a question. We know that the iron 2 oxidation can only happen that fast if microbes are doing it. The arsenic could be microbes, or it could be the iron 3 that's produced here could be oxidizing the arsenic, because that happens too. We also know that when iron 3 oxidizes arsenic 3, that it's catalyzed by sunlight. So we repeated the same experiment in the dark of night. We got the same results. So that suggests that it's really microbes and not an abiotic oxidation. Thioarsenates are very important and very difficult to analyze. They're both thioarsenites and thioarsenates. So thioarsenites you can think of as if you have arsenite, ASO3, and you start substituting sulfur for each one of those oxygens. And you get mono, di, and trithioarsenite. This last one is hard to do. And you also have, because of the way the bonding occurs in arsenic. Thioarsenates are also possible where the sulfur substitutes for the oxygen in those. And the last one, ASS4, is also very hard to do. In fact, I don't think anybody's made the solid material of that yet. This is the second natural water on the planet that we found thioarsenates in. This was very nice work by Britta Planer-Friedrich, and she's one of the leaders in this whole analytical enterprise. And this is a key diagram from that paper that was published in ES&T. A lot of stuff going on here. Just look at first, this is the total dissolved arsenic line. It's increasing because in the overflow of the water, it's evaporating rapidly, so the concentrations go up. So that's why it's increasing a bit. But here you notice that the next highest concentration on here after the total arsenic is trithioarsenate. And then you have arsenite. And then as the hot spring overflows, the triarsenate gets oxidized, it goes down, and the arsenite increases. And then finally, the arsenite starts going down because arsenate is increasing. Very complex chemistry going on here. The important thing is that these thiocomplexes form whenever you have arsenic and sulfide. And that means in any reduced sulfide-rich groundwaters, it'll keep the arsenic dissolved. It's not going to precipitate very easily. Here's a place that Ann Mace has been to. Mono Lake, pH 10, has about 3 times the salinity of seawater. Arsenic concentration gets up to about 20 milligrams per liter because of geothermal inputs into the sediment, and oldest lake in North America. And this was the first place where thioarsenates were shown to exist. And that's it. Thank you very much. I got to stop there anyway.
Thank you, Kirk. Nice pictures from Yellowstone.
We have some questions.
I don't know if I should get off the screen or not. But, yeah. But, well, okay. Yeah. Okay. Yeah. Questions, please.
Yeah. Here I'm going to read one that's in the chat. This is from Ayas Alam, the director of the geology department in Universidad Atacama here in northern Chile. And the question is, my query is how, on one hand, you consider some rhyolitic rocks as likely source of arsenic in Iceland, which is quite interesting, while no such criteria was used for East African Rift, both being predominantly basaltic domains.
I'm not sure that I would agree with the characterization of the East Africa Rift as being mostly basaltic terrain. There's a lot of silicic rock out there and volcanic rock in sort of the rhyolite to andesite range. And in addition to that, there's bound to be some sediments in there, and where there's sediments, there's probably some shales as well. So I haven't looked in detail at the lithology. That would be useful. But they're not all basalts for sure. I guess the other thing I should say is when you're making a rift valley, there's also a lot of sediments that are falling into it. And those also tend to be more silicic type of sediments through which the hydrothermal solutions are going.
Yeah, I don't see more questions. I don't know if
I have questions. I can bring them.
Yeah, I have a question.
Okay.
That you mentioned that in Yellowstone, one of the rivers, arsenic is not precipitating because there is a lot of silica precipitating on the channel of the river, and so that will. I mean, if we will have iron precipitating, then we could sorb arsenic. But in this case, arsenic is soluble because there is nowhere arsenic can precipitate.
Yeah, it's just the wrong surface. Iron is a great surface for absorbing arsenic, and silica is a terrible surface. That's right.
Mm-hmm.
Kirk, I have a question.
Rosun, go ahead.
Yes, I mean, I'll come back to the East African. That means I have both my computers on with this. Okay. So the question was that when you look into the East African Rift Valley, we have very limited information about the composition. So the only study which has been done that's primarily in this region, what do you call it? Partly in Ethiopian Rift region and also partly in Kenya. And right now, what we are seeing in Tanzania, for example, there we see that we have gold mineralization area in Gold Mara and Gator Mine region, where we have highest arsenic concentration in the waters, surface waters. So in general, we see it is very poorly characterized, number one. And number two, together with this arsenic, which is coming primarily is thought now that it comes from the gold mineralized belt. But no concrete information is available for arsenic in the Rift Valley. So to say, in the stretch between Ethiopian Rift and down south, like Gold Mara region and also down south Kilimanjaro and further south to Arusha. So do you have any specific tips so that we can follow now when we are investigating?
Yeah, well, first what you do is you settle the political and social problems of East Africa, and then you go in with the army of geologists and map the hell out of it.
Yeah. And importantly, the major focus has been on fluoride.
Yeah. Yeah, there's been much more work on fluoride, that's right. And it's too bad that a lot of those good studies on fluoride didn't analyze arsenic at the same time. But slowly they are being done, and they are finding arsenic is often high where the fluoride's high.
Exactly, and that is also aligned with the findings from Argentina, for example, where we have high arsenic region in Salta and south in Santiago del Estero. For example, we have high concentration molybdenum, vanadium, arsenic, fluoride, and boron also to some extent.
Yeah,
all geothermal
indicators. Yeah.
Yeah. You have an excellent presentation.
You've heard the expression, when you're hot, you're hot.
Yes.
Well, we have another question from Jorge Aceituno. Is there any differences in arsenic concentrations in magmas of andesitic basaltic composition compared with the rhyolitic ones?
Yeah, absolutely. That's what I was trying to show in listing the different major rock types. As you go more and more mafic in your rock type, and that usually means you're going more and more towards your mantle material, the arsenic concentration decreases. That's very clear. So a dunite is a kind of ultramafic rock that is representative of mantle material coming up, and that has almost no arsenic in it. So that's one extreme. The other extreme would be a shale or a magma formed largely from a shale. Okay, we got the questions up here and we're looking at them. Oh wow, so many English speaking people.
Yeah. Dina Lopez, she's asking in the
Yeah.
table for arsenic. Do you want to see or do you want to read?
No, I can see it. I can see it.
Okay,
Yeah.
go.
So in the table for arsenic composition of rocks, volcanic rocks show considerable lower levels of arsenic than sedimentary rocks. Does that mean that the arsenic that we see in hydrothermal waters is not leached from the volcanic rocks, but from some deeper sedimentary source underlying volcanoes? Well, the important point here is that we actually just don't have very much information on certain trace elements like arsenic in volcanic rocks, number one, generally. And secondly, that I'm not this kind of a geologist, so I don't know. But it seems to me that a very challenging question is, where did your volcanic extrusives come from? They could have come from a melted granite. They could have come from a melted sedimentary rock, and they could have come from all different kinds of sedimentary rocks. So what it came from is going to have a large bearing on how much arsenic it's likely to have, unless it's been so leached over a few million years that the arsenic got leached out of it. So the picture is complicated. And at the same time, you can sort of see, you can make your argument any way that you want to when you don't have the data. But you know, if you see, let's say a rhyolite and you see it's very low in arsenic, does that mean it was leached? Or does that mean it just didn't have that much to begin with? And that question hasn't really been asked very much. So we haven't thought about it. All right. If you have a follow-up to that question, I'd be happy to answer it. Meanwhile, I'll go on to the next question. Oh, yeah. How to explain the high concentration of arsenic in caldera lakes? Maybe we should back up a bit and say, where do you see caldera lakes? Now, I know I've seen them in Argentina, and Alaska and a few other places. And these are largely rhyolitic to andesitic terrains.
Costa Rica.
Costa Rica, yeah, very good. Yeah, thank you. I don't recall ever seeing a caldera lake in Hawaii, for example. I'm not sure it exists. So again, this is a good question that I don't think people have thought about too much, but I would say let's look at the rock type and the composition of the caldera lake as well. You know, is it high pH, low pH? A lot of these things are low pH and they can dissolve a lot of trace elements when like the Poas crater in Costa Rica is a good example. Very low pH and can dissolve a lot of trace elements that way. So I think it's a combination of the original rock type and the composition of the water.
But Kirk, is there any absolute apparent benchmarking of the composition of this caldera lakes, so that because it is also thought that they also give an early early indicator to upcoming volcanisms with a change in composition with time.
Oh, monitoring? Yeah,
Monitoring, yeah.
yeah,
Early
yeah.
warning system.
There are some places that have been monitored over time, and the main reason for that is to try and figure out when the next eruption might be.
Yeah, I think sulfur dioxide and sulfur.
Right, there's different sulfur species,
Yeah,
including polysulfides and
yeah.
thiosulfate and weird stuff like that. But I don't know of any, there must be some arsenic data, but I think they've concentrated on the sulfur species, not arsenic so much.
Hmm.
We
Yeah.
have a lot of questions.
So, yeah, okay, Prasoon says volcanic ash do contain the mobile pool of arsenic and co-occurring geogenic trace elements, and that exactly right. So when you have your more silicic or felsic
Yeah.
kinds of eruptions, they put out a lot more ash than lava flows, and especially in the initial stages of the eruption. And so volatile elements will absorb onto that ash like arsenic and other trace elements, and they can be concentrated there. And then when they fall out, as Prasoon and many others have investigated, that they form a large deposit someplace, and then the groundwater goes through them, it'll start leaching some of that stuff off. So yeah, that's a very important tool.
And besides, we have also investigated in the southern Popo Basin where we have this rhyolitic domes, and that's where we postulated that is the southern Popo Basin is one of the locations of natural arsenic in the Popo Basin, in Altiplano. So there also we have both the things. I mean, if we go in.
Yeah, there's another question here from Pablo. And the question is, have you seen differences in arsenic concentration among different types of epithermal deposits? And the answer is yes. And again, I don't know if this has been categorized by anybody or investigated any further, but there's certainly the arsenic content can vary among the same kind of temperature pressure regime for a mineral deposit. And something that's also related to this that's interested me is how come you don't see arsenopyrite forming at low temperature in sediments, and it's most commonly in high temperature mineral deposits or rocks. And I think there's a couple of reasons for that, but if arsenic is so volatile, why during a magmatic intrusion, why doesn't it all sort of come up to the surface or near the surface before it precipitates? And I think one of the answers to that is that some mineral deposits form where there's intrusion, but there may be a very thick cap rock. It could be a thick sequence of volcanic lava flows, or it could be quartzite or something else. But if you have a cap rock that can sort of hold it in, then those minerals gradually crystallize over time from a high temperature and pressure. They slowly will cool off, crystallize, and the arsenic gets trapped in there as arsenopyrite and other possible arsenic minerals. But I don't think that's as common as the near surface type of deposits.
Kirk, before we continue with the next question, we have prepared a survey. We are going to send some questions to the participants, like where are they from and what would they like to learn about arsenic. So just they can ask while we continue the discussion, the question and answers. That's
Okay.
it.
Okay.
So the next question from Israel Labastida.
Yeah, which is the role of the calcium arsenates in arsenic retention? Is it possible their formation in carbonate environments? It's certainly possible in carbonate environments. The calcium arsenate minerals that I know a little bit about have formed in smelter waste situations. Where, for example, an old smelter, they might have taken the fumes from that and put them through a calcium hydroxide slurry, and they wanted to capture the sulfur dioxide and get rid of that. But at the same time, they were capturing arsenic, and then those, when the smelter was abandoned, those wastes just lay on the ground, and people. This is one place in Mexico I'm aware of where they've analyzed the minerals and they found 2 or 3 of these calcium arsenates. They're kind of rare. I think there's also calcium arsenates in the Tsumeb arsenic deposit in Namibia. There's a whole book chapter by Rob Bowl, who worked at that mine many years ago, and the most extraordinary range of arsenic minerals are found there. Some of them are unique to there. And there's some of these calcium arsenates there as well. And if you read his chapter, then you'll learn as much as anybody knows about natural calcium arsenates forming in a mineral deposit, which is not a whole lot. I mean, he does a good job in interpreting the data, but it's very difficult to figure out why in this one place did all these minerals form? Why was there so much arsenic in this one spot that we know of? So that's a good question that we're still struggling with answers. Next question, how do you explain high arsenic concentrations in a periglacial environment with water coming from springs and rock glaciers? Could it be related to redox processes in the geoform? Yes, redox process is undoubtedly important there where you have reduction going on. There's places in Minnesota and Wisconsin where you have a lot of leftover glacial material, which has been releasing arsenic into the groundwater. And as you know, when you start scraping crystalline rock and mixing it all together at the bottom of a glacier, and then you dump it in a moraine sometime later, it's hard to know where it all came from. And it's a huge amount of work to try and sort through that mess and figure it all out. But there's source material that came from some distance in that stuff. And then partly through reduction processes, a reducing environment, there's undoubtedly organic carbon in there that helps to reduce the arsenic and help to mobilize it as well. So that's right.
Okay.
Yeah, I see from Leonardo.
Leonardo, yes. He was asking on YouTube, and I just copy the questions and paste it here.
Okay. What is my opinion on in situ remediation technologies for endotrital aquifers? Oops, then it moved. There. For example, oxygenate an increment of endotrial, yeah, okay. Such as oxy hydroxides by iron chloride solution. I read about medium to low efficiency in alkaline aquifers. Yeah, whenever you have, when you're trying to absorb arsenic out, if you have high carbonate, high pH, and or high phosphate in that aquifer, it's going to be much harder to absorb the arsenic under those conditions. So either you have to change the chemistry, lower the pH, or take out some of the carbonate to make it better, or you have to find a different method to do that. There was when I went to the arsenic and groundwater meeting in Dhaka in Bangladesh back in 1998, there was an engineer who got up who had worked with some of the Bangladesh water. And he said, well, you know, it's easy to take out arsenic. You just add an iron flocculant or aluminum flocculant. But then he was an honest guy. And he said, we tried that with some of these waters. Normally we get about 90% efficiency. But here we only got 65 to 70% efficiency at the most. And what he didn't know was that there was so much phosphate in that water that it was competing with the arsenic and the sorbent wasn't working as well. So these are things that you have to watch for. It's, you know, there are apparent easy solutions, but when you actually do the bench scale testing, then you discover there are problems, and you have to test for a variety of things that might occur in the particular environment or groundwater that you're dealing with. Prosoon is back again in the line or role of Wolastanite.
Wolastanite, yes.
You tell me what you know about Wolastanite.
Because that I don't know, because I think you have seen a couple of your very old publications or somewhere, because I was talking to one of our previous research scholars about this in connection with retention of to contain phosphorus in natural eco-sanitation perspective. So wolastanite are commonly used to, they actually sequester phosphorus also. So the silica phosphorus. Do you think arsenate can also?
So you say somebody did some experiments with that, and
yeah, but in natural systems it is very poorly understood, I think. So
yeah.
it can also be contained when you have calcium carbonate in a system. So the old publication of Jerome Riago, I think 2003 publication, where he talked about, and with Lee or someone, that environmental science and technology paper, and the role of carbonates in sequestering arsenic 3. Do you remember that paper?
Yeah, it's interesting. So there's a question from Cecilia. We found low arsenic in acidic catchments, acidic volcanic lakes, and high arsenic in circumneutral lakes, catchment lakes. Is there some other cations like iron we have to consider to analyze the cause of its differential availability? You are right. In acid waters, you have to look at iron and the redox state of that iron. If the iron's oxidized to iron 3, it will precipitate and it will capture a lot of the arsenic and take it out. Jessica and many others have seen this in acid mine drainage. You can have high arsenic in acid mine water at the source, but once that dissolved iron oxidizes and precipitates, it scavenges a lot of the arsenic and takes it right out. And so that's probably the main difference.
Yes,
Dina,
yes.
yeah, Dina is back. Okay. We're using a lot of phosphate fertilizers around the world. We know that phosphate can replace sorbed arsenic in soils. Has anybody done work in arsenic replacement soils of volcanic regions of Latin America? Well, that's not a question for me. Yeah, that actually brings up an interesting problem. If we put a lot of phosphate into the soils and there's any arsenic in the soils, we'll mobilize more of that arsenic for sure. And vice versa. The reverse mechanism was done by Lena Ma, the lady, one of the first people to show that there are certain kinds of ferns that are hyperaccumulators of arsenic. They can accumulate arsenic without any problem up to thousands of ppm, which is quite phenomenal. I met her once shortly after her paper came out, and I asked her the question. Oh, she did an experiment where she added increasing amounts of arsenic to the soil. And she noticed that as she did that, the ferns grew faster and better and taller and so forth. And it's like, she didn't understand why that was happening. And I said, well, maybe you're adding the arsenic and it's releasing phosphorus from that soil, which is making the plant grow better. And later she tried that and she said, no, it doesn't seem to be working. And then after that, I saw her once more and she said, oh, you're right, it works.
So another question from Prasun.
No, this is not a question, this is just an info on the, I mean, since Kirk was talking about removal of arsenic in high iron systems, and this is how what was done through this arsenic reduction. The Dutch water industry is following the removal of arsenic down to 1 microgram per liter. This is being projected as one of the now the current forthcoming standards for drinking water arsenic in the Netherlands.
Oh, thanks, Pursuit. I'll take a look at that.
Yeah. I think the Jan Zeng's commentary on Michael Berg and Podgorski's paper, she has actually referred to this one, the latest one in Science.
Okay.
Yeah.
There's a question from Maurizio.
Yes.
In Oruro, we collected coral limestone, which had around 10 milligrams per kilogram. Seems high compared with references. Question is how coral limestone can get that high arsenic.
Interesting.
Yeah, I don't know. I mean, I'd have to know a lot more about your limestone to help you answer that question. So there could be a number of reasons.
One question, is this coral limestone Paleozoic or which age?
Exactly. Yeah. What's the age of it? Do you have the age on that, Mauricio?
No, I don't have. I know that it's. I'm not sure about that, but I can get the information later.
You can get the info, yeah.
In the Puna, in the Argentinian Puna, there are some limestones, and they are from Cretaceous, and they are related to the rift from the Cretaceous age, and or maybe I don't know, maybe they could also be from that period.
Mm-hmm.
Sorry, is it related with the, we have in the Altiplano these paleo lakes, which was around 20,000 years ago. I'm not sure. Is it related with that period?
Okay.
So there were coral limestones there?
I'm not sure the limestones from the Holocene and from the Paleo lakes are a lot younger than the Cretaceous basin. Maybe are older. I don't know. We should check on geology, the geology of the place.
Okay, so I think we don't have more questions.
There's one in the, I don't know if you answered the one that's in YouTube or not.
Yes, I already did it.
Okay.
And so, okay, we have another question from Cecilia here.
Do you think that there is some geochemical reason why arsenic is concentrated in borite deposits like arsenic sulfide? I have not looked at borate deposits, but the one thing we do know is boron is one of those geothermal signature elements. So there's 4 geothermal elements that typically go together: lithium, boron, arsenic, and fluoride. And there's some, I mean, I've not looked into this again, but there's an interesting question of just how these rather important borate deposits are formed at all. I haven't studied that. I'll be the first to admit it. But I'm not surprised to find some arsenic, high arsenic associated with it. What the form of the arsenic is, I don't know, it could be sulfide, or it could be arsenate, or something else. But in a big picture, there is a geochemical reason, yes. But then one has to look at the more detailed geochemistry of the particular deposit to figure out just exactly what's going on. Oh, you found it as arsenic sulfide. Okay. Now, which arsenic sulfide? Orpiment? Realgar. Ah. So we know a little bit, mainly, okay. We know a little bit about the relationship between realgar and orpiment as framboids. Huh. Now that's very interesting. So have you published on this? Ah, okay, that's good. Okay. Uh-huh. Can you send me that paper, please? Thank you. Yeah, that's very interesting. That's adjustments.
Okay.
Okay, do you think we're done?
Yes. Yeah, I think so. Jessica, you have your microphone off.
Yeah,
Yes.
you're on mute. Oh, there we go.
Okay. Yes, I think we don't have more questions. And what I wanted to mention is that after your talk, Kirk, I think now we all have can understand better why we have so high arsenic in the Altiplano Puna. Because after seeing on all these pictures of the ring of fire of the Pacific Ocean and understanding that how these plate tectonic borders, these orogenic borders can contribute to high arsenic in the upper crust, and then how this arsenic goes to groundwater and is affecting people. And I think it was super interesting, and what it helped us to understand and to have that every time we go to a place, we have to have in mind the tectonic plates and the context. And so that is, I think, is the highlight from your presentation.
I see a message from Maria Armienta, and if she's still there, thank you for Maria. She's an excellent geochemist and arsenic specialist also.
Okay.
I'm going to start the YouTube, and well, thank you all for attending, and we see you next month.
Yes, the next presentation will be by Mauricio Armachea, and he will be presenting